Now, some fundamental principles to go over for this lab are the Beelzebub law, which basically relates the magnetic field at a point to a current element or a point charge, and that's described here. The magnetic dipole, which represents the magnetic field produced by a magnetic dipole moment at a point, and a magnetic dipole moment is basically some element with that either has a charge or a current flowing through it that causes the electrons around the nuclei or around in these atoms to spin, creating a magnetic field. And so this kind of calculates that magnetic field at any point. And the magnetic distance relationship, which is that as you get farther from a magnetic dipole, the strength of the magnetic field will fall off. And so that's described by this formula here, which will come up later in our graphs. Okay, so the procedure for this lab was quite simple. First, we had to orient our phone orthogonally to the North Pole, so that way the magnetic field of the Earth wouldn't interfere with our calculations. Um, then we had to determine the position of our magnetometer, which we did by measuring its distance vertically and horizontally, and based off the readings we got from our magnetometer, we could pinpoint where it was located on our phone. And then from there, we took some different readings of the magnetic field at different distances, as well as what distances were needed to get certain magnetic field strengths. Hi there, my name is David Gardner, and this is my lab report for Lab 4 about bar magnets. Now, the purpose of this lab is to measure the distance-dependent magnetic field of a small bar magnet, and after taking measurements, we will compare it to our calculated simulation. And also for this lab, the system will be the bar magnet while the surroundings will be everything else. So here's our data. It represents the on-axis distance to get certain magnetic field strengths, those being 20, 70, and up to 220. And so from this slope that we created, we could find the n, which is this value, which is the slope, and the k, or the natural log of k, which is this x-intercept. And from that, yeah, like I said, we basically took e to the power of our slope, and we found that to be 2.8 times 10 to the negative fifth. Then in order to solve for the mu, we relate these three formulas from the start, and that allowed us to find mu, which basically if we take r as 1, we can basically just divide this by 2 to get 1.43 times amperes per meter squared. And so then we had to do the off-axis measurements. Basically what we did is we went a certain distance horizontally and then vertically, and we recorded the B fields at those positions, which are shown in the table up here. And so yeah, for our computational model, we had our input variables, which would be this perpendicular variable and the magnitude of our magnetic field that we both found earlier. And we also had this distance variable to determine basically the radius of what we want to draw. And so we had two on-axis, two on-axis arrows that represent the on-axis magnetic field, and four off-axis arrows, which there are two right here, but it's hard to see from this angle. And there's also a 45-degree arrow represented by this purple. And so based off our observations, we can say that 1 and 4 are true, as when the magnetometer is far away from the magnet, it measures near 0 in the x direction, since it's that far. And for 4, as it moves closer, the measure x component increases. And number 4 and number 2 contradict, so this has to be false. And since the magnet is increasing, number 3 cannot be true. And so just to discuss some what ifs, if we had not oriented our experiment to compensate for the magnetic north, the magnetic field of the Earth would have interfered severely with our data. And if we were to stick two identical magnets together end on end, the magnitude of the magnetic field would be twice that, since they would both be influencing in the same direction. Both magnetic dipoles would be in the same direction. Here you can see our potential sources of error in assumptions as well. One major source could have been the electronic interference of other devices, so that could be smartwatches, phones, or just even like the lights, anything electronic could have a potential interference as it generates a magnetic field. And our second big error would be our magnetometer, as we may have incorrectly identified the position. And we also have made an assumption that the bar dipole, the bar magnet behaved exactly like a dipole, when in reality it could slightly differ from at different points in time.